All right, we're going to get into semiconductor materials and how they are made, and we're also going to talk some about what kind of structures the material uses. We have to spend a good deal of time talking about what makes up a semiconductor, because that is really what makes them unique and makes them work the way they do. So we have to spend a good deal of time talking about the environment in which the electrons move. And it takes 3 chapters to get through enough information so that we know how to figure out how many electrons are available for conduction. So it's very different from other courses where we dive right in and start talking about devices. So when we're talking about materials, we basically just look at the electrical properties and the characteristics of semiconductor materials and the devices made out of them. The electrical properties are determined by the chemical composition of whatever particular material you're using, and we'll talk a little bit more about that, and how the atoms are arranged in the solid. And that also we will talk about quite a bit. There are all kinds of materials that are used in electrical devices. Conductors carry large amounts of current. Insulators can actually have a lot of voltage across them, but they don't carry any current at all. Dielectrics we use in capacitors as kind of fill between two charges. And we also use magnetism to make things work. However, most of what we do in this class doesn't involve most of these things. We do actually make capacitors in here, but they're not the kind of capacitors you're used to seeing. They're really kind of different. But a capacitor just involves a separation of charge and something in between it. And quite frequently, semiconductor devices do that, where they have a separation of charge with something between it, so you end up with capacitance by default. I wish I would stop doing that. Okay. So we find semiconductor materials in a particular part of the periodic table, which is, I guess, why you have to have chemistry before you take this class, although there really isn't much chemistry involved in what we do. The general area is right kind of to the right of the middle, and it involves groups. We name them kind of, I know they have other numbers in front of them, but basically we just call them 2, 3, 4, 5, 6, because that is telling us how many electrons are in the outer shell of the material. And that's what's important for making semiconductor devices. So we can, I don't like this thing at all. There we go. We can make elemental semiconductors. Elemental semiconductors are made out of one type of material, and there's really only 2. Silicon and germanium make semiconductor substrate upon which we can create all kinds of devices. And those are really the only 2 elemental semiconductor materials we can make. And silicon is much more common than germanium. Germanium has a lot of good characteristics, but it is more expensive, and it's actually harder to obtain. So there are some really good characteristics of germanium devices, but silicon is generally just used more. It's cheaper, and ICs are all made out of silicon, so silicon is usually the basis for semiconductor materials. Not all of them, though, just the ones that are kind of made on a chip, a lot of them, because they're made out of silicon. Another way that we can make semiconductor devices is we could combine 2 elements, and we can actually combine silicon and carbon, and we can combine silicon and germanium. And those are compound devices, but they aren't necessarily elemental. So carbon is only used as kind of a part of a semiconductor. We don't make semiconductors out of just carbon. It would be awesome if we could, because they'd be really, really tough, but there are reasons why we don't. So sometimes silicon carbide and silicon germanium are used as elemental kind of semiconductors, but not so common. The other way that we can make semiconductor devices is try to create a situation in which we have a similar thing to silicon or germanium. The reason why we use silicon and germanium is because they have 4 valence electrons in the outer shell. They would like to have 8. Therefore, they share electrons and make a particular structure based on the fact that there are that number of electrons in the outer shell. So what we can do is we can actually make other devices if we kind of spread out from that group 4 column and go out in both directions at the same time. So we can combine elements from groups 3 and 5 and get the same kind of effect. We still have a sharing of electrons. It's just some of them are 3 and some of them are 5, but they make a structure in which that's very similar to the structure that silicon or germanium by themselves make. And gallium arsenide, which is GAAS, is probably one of the most common compound elements that is made. They're actually quite useful in LED manufacturing and other types of devices that require light emission, and there's a reason why they're better than silicon for that. We'll get to that later. We won't get to that now. So we can make base elements out of group 3 and 5 materials, and we can also go even further out and go to group 3 and 6 and make some there, like cadmium sulfide and those types of devices. So we can make a lot of different combinations to come up with materials. We can also make something known as ternary compounds, which use 3. And when we do that, we'll basically take 2 elements from one group and 1 element from another group. So in this case, there's aluminum and gallium, and they are proportioned so that the amount of gallium and aluminum together is going to be the same as the amount of phosphorus. So that's why it says an X under aluminum and a 1 minus X under gallium, because it's proportioned so that the total between the two is going to be 1, and then the phosphorus is a 1 also. So you might have proportions such as 0.6 aluminum and 0.4 gallium, and then 1 phosphorus, and extend it on out, and you can make that. You can also make a compound where group 5 is split up, and you have just gallium, and then you have arsenic and phosphide, and those two are combined so that they make a compound that comes out equal. Even further, we can make 4. I held up 10 fingers for 4, but it's late in the day. So there was a time over the summer when I got really mad and I wanted to give someone the finger, and I discovered I can't do that with my left hand. Evidently, I don't do that very often. So my hands don't work really well. It's probably a terrible thing to tell you guys, but anyway, I tried, and my hand wouldn't cooperate. And by the time it would, it was too late for the effects. So anyway, you can make 4 compounds where basically you take the group 3 and proportion it, and the group 5 and proportion it. You can do the same thing with several compounds. And the reason that this is done, and we really don't talk about how this is done until way, way, way later in the course, but the reason we do this is because you can tailor a compound to have very, very specific characteristics by doing this. So the proportion of different elemental devices that go into making the material is proportioned in order to do something very specific. And this is one of the many, many reasons why semiconductors are so different from other types of devices. Because if you have a conductor is a conductor, and it conducts. If you have an insulator, it insulates. A semiconductor can be made to do many, many things and have many different characteristics. So if we look at insulators, you know that insulators don't conduct anything. Most of you know that, even if you haven't had circuits, pretty much you know that an insulator is what doesn't allow current to flow. And good examples of insulators are like nickel oxide, glass, quartz, things like that. And you notice they have very specific values of resistivity. Resistivity is just a characteristic that goes into determining how much current is impeded. So if you have a very high resistivity, you don't get any current flowing. Conductors have very, very, very low resistivities and just allow current to flow pretty much at will, and that's good. Semiconductors, on the other hand, have a range. That's one of the reasons that they are different, because they can have a range of resistivity depending on how they're manufactured. So they mostly fall into kind of the same range of resistivity values, but for the most part, they can be anything within their range, depending on how they're manufactured and then what else might be added to them. So this is something that makes semiconductors unique. The resistivity or conductivity, those are just opposites, can be varied over orders of magnitude. Not just a little bit, but a lot. You notice that for silicon, you have resistivities from 10 to the fourth, almost to 10 to the minus fourth, and that's like 8 orders of magnitude almost. So that's a lot. And that's one of the reasons that they are different. How do I make this stop doing that? I don't know. I get this like keyboard that pops up every time I want to go to the next slide. It's very annoying. So, as I said, you can have a range of resistivity over several orders of magnitude. And I did explain what resistivity was. You learn about that. Don't you in Circuits 1 learn about resistivity, or do you not? No.
They touch on it.
Do they don't tell you rho L over A, evidently. I have found out. I don't know why they don't, but they don't. But that's how you calculate the resistance of anything, is you take the resistivity times the length and divide by the cross-sectional area, and that gives you the value of resistance. And so materials have resistivity, and how much of the material you have tells you what the resistance of it is. Kind of simple. I don't know why they don't teach that. Anyway, the 4 valence electrons from elemental semiconductors causes them to form a particular type of structure. It makes them form a crystal that is very specific in its design, and the construction of that crystal is what makes semiconductor materials possible. So let's see, maybe this works better. Okay, I'll use this. So there are several types of solids that you can make out of pretty much anything. You can make something that's called amorphous. An amorphous solid has no particular order to it whatsoever. A good example of that is glass. You heat up glass, it gets all molten, and then it solidifies before it has a chance to form a structure that's kind of, orderly, I guess. It just solidifies too quickly. So because of that, it doesn't have any particular atomic arrangement as such. Most materials that form crystals form them in something known as polycrystalline structures. So most crystals that form naturally, that's what they do. They have areas of order, but they're divided up by these boundaries called grain boundaries. And the problem with grain boundaries is we can't have that in semiconductor material because that blocks the flow of current. So current flows really well through the orderly parts, but then when you get to a boundary, it stops, and you can't do anything else. So what we like for semiconductor materials is basically a single crystal, where there's a bunch of order all the way through the device. And that's not the easiest thing to obtain. It can be kind of difficult because they don't occur naturally that way. So crystals can come in all different shapes and sizes. You notice that salt and bismuth and gold and brown sugar form kind of different shapes. You'll notice that silicon is actually pictured as a kind of a silver thing. And that's what it actually looks like when it forms a crystal. It's actually kind of a silver, long, cylindrical thing that we will talk about how it's made in a little while. But basically, silicon makes a structure that is unique and can be used to do many things. Let's see, keep things ordered. There we go. So we need a single crystal solid to make a semiconductor work. No polycrystalline, no grain boundaries, no nothing. We mostly use silicon. As I said, germanium, gallium arsenide are also used, and other types are used depending on what the electrical characteristics might be. So, how do we make them? Well, if you want to make a single crystal of silicon, you have to manufacture it specifically. It doesn't occur like that in nature. Polycrystalline type material does occur, but single crystals don't. So the oldest and pretty much the most common technique we use is something known as the Chokrolsky method of making silicon. And it's actually kind of an interesting story. There was this guy, Chokrolsky, who lived back in the 19th century. He was born in the 19th century, but then he also lived into the 20th century. And he was a Polish chemist. And he studied how different types of metals crystallize. That was kind of his thing. And one day, he was taking notes. And this was over 100 years ago this happened. He was taking notes. So back then, they actually had an inkwell. And he stuck his pen into melted tin instead of the inkwell by accident. And when he pulled the pen out, he noticed that there was a thin thread of tin attached to it. And when he studied it, he found that there was actually a single crystal connected to it, rather than a polycrystalline. The whole string was actually one single crystal. So he published this a couple years later, and he just basically said, hey, this is a great way to make single crystals. We can, dip something very small in there and pull it out really slowly, and we'll make these crystals, and it'll work really well. And then what ended up happening to him was he ended up, after that, he continued his metal research in Germany and Poland, and then after World War II, the Polish government said, hey, you worked with the Germans, so we're going to take away your professorship, and he ended up opening a cosmetic and household chemical shop until he died in 1953. So that's what happened to him. But, and this is why one should always know that most discoveries in science are not made purposefully. They're usually and quite frequently are made by accident. And that's what happened here. It's just a complete accident. But later on, right before he died actually, two scientists from Bell Labs used his method to make single crystal germanium. And later on, they used this to make silicon and gallium arsenide. And we still use this method today to make single crystal silicon and germanium and gallium arsenide and all the different types of semiconductor materials that we use. So what actually is done to make this work? Well, first of all, you get a kind of a quartz crucible because we can't contaminate the material with anything, so quartz is just silicon dioxide. So a quartz crucible is taken and a bunch of polycrystalline silicon is put in it and melted. And after it's melted, they add something called doping impurities, which we'll talk about later, but if those need to be added, if impurities need to be added, which sometimes they do, well, frequently they do, those are added to this kind of melted silicon. And then what happens is a seed crystal is just lowered into that vat of melted silicon, and turned. So as it's turning, it's pulling really, really, really slowly, and the silicon is crystallizing first around that one tiny spot, and then later it spreads out because it's turning really slowly and it's just kind of growing. And as it pulls out, of course, less and less is left in the bottom, and what you're left with is a boule of silicon with a little bit of residue at the bottom. I hate this thing. So what it looks like is, and they can be really big. So these are not small. They're big, like 6 feet long, and like this big around. They're huge. But basically, the silicon crystal that comes out looks pretty much just like this, and some oxygen is left, and basically a high temperature coil is just passed up and down it, and it causes the impurities to get pushed to the end, and then they're just chopped off. So that's basically how they purify it, is they just run a coil up and down it. Then what happens is a flat edge gets ground along one side, and the reason for that I will talk about later. I'm not going to talk about it right now. But it's in a particular direction, and that basically indicates, that flat edge indicates when you get the whole flat wafer, when it's cut off, where it will split. So it gives us a starting point to split it. And again, I'll talk about that later, not right now. So this is a general overview. So the wafer is cut up, and oftentimes nowadays there aren't necessarily flats that are really obvious. Sometimes they just use notches, but in the old days they always made kind of a flat along one edge. And then it's cut up, and then you end up, and actually I can send this around so y'all can look at it. You end up with something like that in a case, yes. Because if it's not in a case, it'll actually, you can actually take that and just break it. So you can just pass that around and look at it. So this is actually a picture of somebody making a silicon boule, and it is from 1956, and actually this is a picture of one of the first places they manufactured silicon, because they started manufacturing them in 1953. So this is really, really, really soon after they kind of started manufacturing silicon. And this is kind of a cutaway of what the puller looks like, and then on the right there's actually a photo of an actual puller. Yes?
What is the seed crystal made out of?
It's silicon. It's just one little piece of silicon, and it's actually oriented in a particular direction, which we haven't talked about planes and directions yet, but it's actually oriented a certain way so that the whole boule, when it comes out, is oriented in a certain way. So it's also made out of silicon. The only other way, well, there's actually some other ways that silicon is manufactured, but I'm not going to go into those. The other method that is used is something called float zone method, and in that you have polycrystalline rod and one seed crystal kind of held together, and there's an RF coil that melts, and it kind of makes the single crystal at the bottom, and it just kind of moves up, and the polycrystalline becomes a single crystal. It's a good method because it's quite pure. There's the problem is it's expensive. So it's not used as much as the Chokrolsky method, basically because it's more expensive than what we use nowadays. So it's a good thing for the production of very, very, very pure semiconductor materials, but not so much for just standard stuff.